Hi, my name is Dongjin, and I'm currently studying on TADF and hyperfluorescence. I will first explain the principle of TADF and the designed blue TADF material. And after explaining the hyperfluorescence principle and materials that TADF is actually applied to OLED devices. Lastly, I will present my thoughts on the direction OLED should go and finish the presentation. TADF is a thermally activated delayed fluorescence which literally upconverts triplet exciton into singlet exciton through heat. TADF can achieve 100% internal quantum efficiency in electroluminescence devices through triplet upconversion. Then how to upconvert the triplet? It depends on the design rule of TADF. The TADF molecules has a molecular structure with spatial separation of HOMO and LUMO as a donor-acceptor type. When HOMO and LUMO have spatial separation, the energy difference between singlet and triplet becomes small. And when the energy difference is usually less than 1 electron volt, triplet upconversion or RISC is possible when in room temperature heat. To add an explanation of how HOMO and LUMO separation reduce the singlet-triplet energy difference, two electrons with different spin states can exist in the same orbital, but electrons with the same spin state cannot exist in the same orbital. Singlet excitons can have two electrons of different spin states in the same orbital, and there is a possibility that electrons exist in overlapping HOMO-LUMO orbitals, resulting in energy instability due to the repulsion. As a result, the singlet energy increases and the triplet energy, on the contrary, as the overlap increases, the two electrons move away from each other and the repulsion decreases, resulting in a decrease in energy. This is expressed as a exchange energy according to the orbital energy, and the formula is as follows. However, although the RISC speed can be increased as the degree of HOMO and LUMO overlap in TADF decreases, it has a problem that it is difficult to capture both at the same time due to the decrease in fluorescence efficiency. I have a successful experience in designing blue TADF molecules with high fluorescence efficiency and high RISC rate at the same time. I set the TADF molecular structure, which has higher local absorption and high fluorescence efficiency. However, this reference has the disadvantage that the RISC speed is slow. To solve these disadvantages, I additionally introduce a benzofuran moiety that can form a steric to the donor moiety. As a result, the TRZ3 molecule achieved a high EQE and a faster RISC rate. By manufacturing this device, the characteristics in EL were identified. All three molecules were measured in an N-type DP-PO host and emitted light in the blue range of 460 nanometer to 470 nanometer. And the max external quantum efficiency of TRZ3 was 23.3%, which was almost the same as the reference. However, in the case of TRZ2, The EQE is quite low, which is expected due to the low PLQI and dipole orientation. The above device is a device structure in which exciton is mainly formed by hole hooping from HTL to TADF using an N-type host. In case of TRZ2, which is deep in HOMO, hole hooping is difficult, so it is expected to show a low EQE. In terms of roll-off, in the case of TRZ3, 44% of the 1000 nit standard was observed through high RISC speed, and the result satisfied high fluorescence efficiency and high RISC speed for the initial design purpose. My current main research topic is hyperfluorescence. Although the TADF molecule described above can achieve 100% internal quantum efficiency, it has a limitation that it cannot be used alone in device due to the wide half-width due to various geometry changes in the excited state. Therefore, hyperfluorescence forms 100% singlet exciton through RISC in TADF by doping the host TADF and final emitter in EML, and transfers energy to the final emitter through faster energy transfer. Therefore, it is possible to realize 100% internal quantum efficiency and high color purity through the final luminous body at the same time through hyperfluorescence. At this time, when designing TADF used for hyperfluorescence, the first thing to do is to have a light emitting area that matches the light emitting area of the fluorescent light emitting body for efficient energy transfer. Second, TADF must introduce a blocking group to control the external energy transfer to the emitter. Finally, TADF should reduce the probability of external energy transfer by speeding up the triplet harvesting rate through a high RISC rate. I am currently developing red fluorescence and have a successful research experience in increasing efficiency and lifetime at the same time by setting 4CZ TPM as a reference. First of all, 4CZ TPM emits lights in the 540 nanometer region and has high fluorescence efficiency. And lastly, the molecule itself is very stable. Looking at the DBP absorption graph below, you can see that the absorption dramatically increases in the 580 nanometer region. And I'm currently focusing on designing a TADF molecule with a faster, uh, with a higher redshift and faster RISC rate than 4CZ-TPN that emits light in the 540 nanometer region. For the first time, by introducing benzocyanocarbazol bound to the 3 and 4 positions of carbazole, we succeeded in making a fast RISC rate by the heavy atom effect. Subsequently, a faster RISC rate was induced by introducing benzocyanocarbazol bound at positions 1 and 2, which can form steric and third butyl carbazole, which has higher donor strength than carbazole. As a result of the TADF single device evaluation, both molecular structure showed excellent roll-off compared to 4CZ-TPN. In particular, in the case of 2BTCZ, 2CZ-TPN, there is almost no roll-off, and a very fast RISC rate can be expected. In addition, both molecules redshifted compared to 4CZ-TPN, and the efficiency of TADF itself by the energy gap law was low. And as you can see in the hyperfluorescence device, the BTCZ 3CZ-TPN device showed high EQE of 13% compared to reference material. Recently, multi-resonance molecules that separate HOMO-LUMO into atomic units using the resonance effect of nitrogen, oxygen, and boron instead of donor-acceptor units are being actively studied. Using these molecules capable of high color purity and triplet harvesting will be developed in the emitter in the future, and the rigid molecular structure will increase reorganization energy. It is small, and the possibility of using it as a host is also open. As such, it is expected that active development of multi-resonance molecules should be made in the future.